Good morning, students. So, here I am with the third part of the same chapter, which is kinetic theory of gases and radiation. But today we are going to see something about radiation in last some slides, and then in detail we are going to study tomorrow. Alright, so let's start with our next part, which is part 3 of kinetic theory of gases and radiation. So let's move towards the next slide, which will explain you what you have done yesterday and what we are going to learn today. So let's recall what we have done yesterday. So yesterday we have done these points, which are pressure which is exerted on a gas when we are going to consider an ideal gas. Yes. And then the second thing which was we have learned was root mean square speed, or you can say this as root mean square velocity also. So which is denoted by VRMS. Okay. Then third point which we have learned yesterday was temperature. The temperature which exert on a gas, which is given by energy per mole. Yes, we have done that expression yesterday. And then next point which we have learned was equipartition law of energy. The law which has been explained by me yesterday was nothing but energy is equally parted to the every particle which is there inside a gas molecule. When we are going to consider about monoatomic gas molecule, diatomic gas molecule, or polyatomic, number of molecules when goes on increases, that energy will be equally parted in all the molecules. Okay, so this is the law of equipartition. Then last and most important point which we discussed yesterday was degrees of freedom. Degrees of freedom we have seen. By using the degrees of freedom we are going to see many applications today also. So try to remind this point, which is degrees of freedom. What was that? Degrees of freedom was nothing but number of coordinate which is required to locate any atom inside any system. So that is nothing but degrees of freedom. So these are the some points which we have learned yesterday. I hope you all got all these points and even the points which we learned in the first lecture. All right, so let's move towards our next slide, which explains you what we are going to see today. So point to be learned for today's lecture. First point that we are going to learn is Mayer's equation. Actually this deals with specific heat capacities. This specific heat capacities you have already learned in chemistry as well as in physics in last year, and even I guess you are doing that in thermodynamics also in chemistry. All right, that we are going to see here today. Then specific heat capacities that I have told you right now. Then the third point which we are going to see is we are going to see the difference between conduction, convection and radiation. So conduction, convection and radiation is nothing but three modes of transfer of heat. By using these three modes, heat can be transferred from one particle to another particle. Now in this we are going to see either the medium is required for transfer of heat or not, that we are going to see today. Right. The last point which we are going to say is absorption, reflection and transmission. These all are the points which we are going to clear today and which we are going to see in this lecture. So let's move towards first, which is Mayer's equation. So what is Mayer's equation? As I have told you, Mayer's equation deals with the relation between specific heat capacities, that is C, molar specific heat capacities, and these are at constant pressure as well as at constant volume. Not some of, many of the terms you have learned in thermodynamic section. Right, so before moving towards this equation, let us remind quickly what you have done in thermodynamics. You have seen equations of thermodynamics, first equation, second equation, and even in physics you have done zeroth equation or zeroth law of thermodynamics, which deals with transfer of heat. And enthalpy, you have seen internal energy. These all are related to thermodynamics. All right, so let's move towards our equation and our point, which is Mayer's relation. So to derive this relation, we have to consider a 1 mole of a ideal gas which is enclosed in a container which is having piston on it. Now what is meaning of piston? A container which is having piston, meaning when you are going to apply temperature to it, and when volume which is inside the gas molecules, when it goes and increases, that piston will try to move in upward direction. So this is nothing but container with piston. All right, so we are going to consider that, and in this also we are going to consider for two terms. First one is at constant volume and second one is at constant pressure. So let's see what happens to it. So first, consider 1 mole of ideal gas that is enclosed in cylinder by light, frictionless, airtight piston. It is light, frictionless, and airtight. Alright. By considering all these three terms, which are pressure, volume, and temperature, we are going to see all the expressions. Now, if the gas is heated so that its temperature rises by dt, right, we are going to increase the temperature of this by dt. Now what happens to the other terms? One of them will be remains same and one of them will try to increase the terms. So here in this case we are going to took constant term as volume. So as the temperature goes on increases by dt, the volume will remains same, so volume is constant. Now what happens to the heat? Yes, obviously heat is created as temperature increases. So amount of heat, we are going to denote it as dq1, because this is the condition number 1 where we are going to keep volume as constant term. So let us consider amount of heat as dq1, and it increases internal energy by dE. We are going to consider the increase in internal energy as dE. As the volume remains same, what happens to the work done? Yes, obviously no work is done because volume doesn't change. As the volume goes on changing, the piston will try to move in upward direction, but volume is not changing, so piston will not move. If the piston is not moving, that means work is not doing, so work done in moving the piston is nothing but 0. So we are getting this equation. dq1 is equal to dE is equal to cv dt, because this is at constant volume. We have considered right here volume remains constant, so this is cv dt, where cv is molar specific heat of a gas at constant volume. Okay, so this is the first equation that we have derived from this. From where you got this equation? Tell me from where you got this equation. This is thermodynamics first law. From there I have got this equation. Okay. Now, if the gas is heated to the same temperature at constant pressure, then what happens to the volume? Now I am saying I am heating the gas at the same temperature. Temperature is same, but the pressure goes on changing or not? No, pressure is constant and volume is changing. As volume is changing, that piston will try to move upward because the volume is changing, so it will create work done. So that work done is nothing but P into dV. Here you can see what is that? dW is equal to P into dV. So second equation is dq2 is equal to internal energy which is being increased, so dE plus work done is there, so dW is equal to molar specific heat at what? Yes, constant pressure, so it is Cp dt, because temperature term is also there. So Cp is molar specific heat of a gas at constant pressure. So I hope you all got both this equation. For the first equation, volume remains same, and for the second equation, what remains same? Constant temperature and constant pressure and constant volume. So we are getting first equation over here, dq1 is cvdt, and second equation is cpdt is equal to de plus dw. As we have said, dw is nothing but pvdv, pdv. We are going to put that in this given equation. So let's see what happens to it. Quickly moving towards the next slide. Yes, here is the second slide. But as we have already derived equation for dE, which is cvdt, here dE is cvdt, right? So you can put this also here and pdv here. So let's see. So but dE is equal to cvdt, as internal energy of ideal gas depends only on its temperature. So cpdt, by putting both the values in equation, we get cpdt is equal to cvdt plus dw. But what is dw over here? It is nothing but pdv. So by taking dt common and taking that cv to another side, we are getting cp minus cv dt is equal to pdv. Now instead of dv, we are going to put, or pdv, we are going to put pv is equal to rt. But dv is there, that means change in volume is there. When volume goes on changing, what changes? Obviously t. So pdv will be rdt, because r is constant, it doesn't change. So we can put dt instead of t, since pressure is constant. Alright, so instead of pdv, we are going to put rdt. So here this equation becomes cp minus cv dt is equal to r dt. So this dt and dt will get cancelled. So you are getting this equation, which is cp minus cv is equal to r. Okay, so as you can see, we have considered cp minus cv is equal to r, right? We have already considered the work done and heat is having the same unit, or they are same quantities, but it is not so, because usually heat is measured in calorie and work done is measured in joule. So both are different. So this relation is then modified into another terms, which consisting of mechanical equivalent of it. So that is nothing but cp minus cv is equal to r upon j. So this is the modified equation of Mayer's relation. Now cp is nothing but MOSP. Now what is MO and what is SP over here? MO is molar mass of gas. You have already seen this. And what is SP? SP and SP are principal specific heats. As CP and CV are molar specific heat, SP and SV are specific heat but principal specific heat. So this is the relation between them. That is nothing but Cp is equal to MOSP and Cv is equal to MOSV. By using both this equation in the above equation, we are getting instead of Cp MOSP minus instead of Cv MOSV, which is equal to R upon J. By taking common MO, we are getting SP minus SV is equal to R upon MOJ. So this is the equation in terms of specific heat, principal specific heat. Okay, so this is all about the specific heat. Now what we are going to do is, we are going to calculate the specific heat capacities for monoatomic, diatomic and polyatomic. Now for that, we have to know what is degrees of freedom and how much is the amount of degrees of freedom, and in case of motion also, that we have seen yesterday. So let's see. Let's calculate specific heat of gases. First is monoatomic. What is degrees of freedom for monoatomic? As it is only one molecule, it can move along three axes, x, y as well as z. So it is having degrees of freedom as 3. Now, what is average energy per molecule? As individual it is having half kbt, right? We have seen in equipartition law, and it is having 3 translational, 3 rotational energies, so it is 3 into half of kbt. So it is 3 into half of kbt, so it will be 3 by 2 kbt. So total internal energy per mole will be E is equal to 3 by 2 Na kbt, because we are considering for mole. So here it is Na, Avogadro's number. Then what will be Cv? We have seen it is nothing but dE upon dt. So 3 by 2 Na kb, dt will get cancelled. So here you are getting, instead of Na and kb, it is nothing but gas constant. So you are getting Cv instead of NaKb R. Alright. So 3 by 2 R. So as you all know the relation between Cp and Cv, what is that? Cp minus Cv is equal to R. Alright. So by putting the value of Cv, yes, here Cp minus Cv is equal to R, that you all know. At Cp is what? 3 by 2 R, or Cv is 3 by 2 R, right? Cv is 3 by 2 R. By putting that value in the given equation, we are getting Cp as 5 by 2 R. And now by taking ratios of both the specific capacities, we are getting gamma. That sign is known as gamma. So gamma is nothing but Cp upon Cv. For monoatomic, it is nothing but 5 by 3, because 2 will get cancelled, right? So we are getting 5 by 3. So this is for monoatomic gases. Now we'll try for diatomic. What happens to diatomic? For diatomic, 5 is the degrees of freedom, right? When 5 is the degrees of freedom, then it is having 3 translational motion and 2 rotational motion, right? So when 3 translational motion is there, so energy is also divided into this type. So as 3 it is there, so 3 by 2 Na kbt, as we have seen over here, per mole we are going to see. So this is 3 by 2 Na kbt, as it is 3 times rotational translational motion and 2 times it is rotational. So plus 2 divided by 2 Na kbt. I am repeating again, the energy law of equipartition of energy states that each molecule is having energy of half kbt. As the number of degrees of freedom increases, it got multiplied to the energy. So the constant term is half Na kbt, and we are just going to multiply number of degrees over here. So as 3 translational motion, so we are multiplying by 3. So 3 by 2 Na kbt is there. As it is 2, then 2 by 2 Na kbt. So by combining, we are getting 5 by 2 Na kbt. Alright. So what is Cv? By dividing by dt, or by dividing T to energy. So we are getting Cv as 5 by 2 Na kb. T will get cancelled because it is divided by dt. Look over here. Yes. So you are getting Cv as 5 by 2 Na kb. Now what is Na kb? R. So you are getting Cv as 5 by 2 R. Now again, putting the value of Cv in Mayer's relation, we are getting value for Cp also. So value for Cp by using that is 7 by 2 R. Now by taking ratio, we are getting value for gamma. So gamma is equal to Cp by Cv, which is nothing but 7 upon 5. It is gamma. I hope you all got that, what we have done in this slide. We have calculated the specific hits for monoatomic as well as for diatomic. Now we are going to consider for polyatomic. It comes out to be a little difficult, but I will try to make you it easy. All right, so let's see what happens to it. As we have seen, polyatomic, that means four or more than three atoms are there, more than two atoms are there, because in case of monoatomic we have considered only one atom is there, in diatomic two atom is there. In case of polyatomic, what happens, number of molecules are there. We are going to consider one example, which is ammonia. Ammonia is example of polyatomic, in which three hydrogen atoms are there and one N atom. What is N over there? Yes, nitrogen. So NH3 is ammonia gas. So that is polyatomic, in which three hydrogen and one nitrogen. So four are there. But what happens over here? We'll consider translational as well as rotational motion in this, but we can't denote or we can't define the vibrational motion of the particles in ammonium. Why is it so? Because we don't know exact geometric structure or exact geometric shape in which it is arranged. We haven't known. Suppose they are arranged at the ends of the cube, then the vibrational motion will be different. When they are arranged in linear form, the vibration will be different. So we are going to consider the number of vibrations as F over here. Alright, so moving towards it, let's consider polyatomic. So E is nothing but 3 by 2 total energy. All will be having, if 4 are there, but all 4 molecules will be having 3 translational energy. So this is 3 by 2 NaKBT. All will be having 3 rotational energy. So again 3 by 2 NaKBT, but vibrational motion we don't know how many are there. So we are going to multiply it by F. And individually, as we are going to consider 4 molecules are there, right? So 2 and 2 will take part in vibration. So here it is multiplied by 2, divided by 2 NaKBT. Have you understood? I am explaining again. Total internal energy, total energy in case of polyatomic is 3 by 2 NaKBT, as between 4 of them all will be moving translational motion in 3 axes. So 3 into half NaKBT is there, so it is 3 by 2 NaKBT. Again all 4 will be having 3 rotational motions, so 3 into half NaKBT, so this is 3 by 2 NaKBT. And we don't know how much vibrational motion will be there, but as it is a vibrational motion, 2 should be come into consideration. So number of vibrations is F into 2 atoms are going to consider, so 2 into half NaKBT. So what happens over here then? Here this 2 and 2 will get cancelled, and you are getting 3 by 2 NaKBT here and 3 by 2 NaKBT. By adding 3 and 3 will get 6 by 2. 6 by 2 will be 3, right? And NaKBT and NaKBT are common, so we are getting 3 plus F NaKBT. I hope you got this equation. 3 by 2 NaKBT plus 3 by 2 NaKBT will be 6 by 2 NaKBT. 6 by 2 is nothing but 3, and here it is plus F. So 3 plus F NaKBT. Okay. So we are getting this as Cv is equal to 3. As we have known, this Na and Kb is nothing but R. So we are getting Cv as 3 plus F into R. By putting this value in Mayer's relation, we are getting value of Cp. It is nothing but 4 plus F R. By taking ratio, you are getting Cp by Cv is 4 plus F upon 3 plus F, because this R will get cancelled. So this is all about polyatomic gas. Now I have done something, one more term, which is there. So this is nothing but for diatomic gas. Now diatomic gas we have done already. So why is it so? Because we are going to consider this is non-rigid. First we have seen for rigid, and now we are going to see for non-rigid. Okay, so for non-rigid, vibrational motion will be there. So 3 translational motion, 2 rotational motion, 2 vibrational motion. So that will be 7 by 2 NAKBT. So CV is equal to 7 by 2 R, CP is equal to 9 by 2 R. So you are getting gamma is equal to 9 by 7. This is very easy. Okay, so this is all about specific heat capacities when we consider in case of polyatomic, monoatomic and diatomic. Okay, so let's move towards our next slide. What does it give? Okay, now it's your turn to think something. So can you tell me how the heat transfers, how the heat travel, and what is exactly heat that you are going to tell me? Okay, I will answer each of the question over here. So what is the first question over here? First question is how the heat travels. How the heat travels? It travels by using 3 modes, either by molecule to molecule, or inside fluid, or without medium. So these 3 modes are nothing but conduction, convection and radiation. So that we are going to see more in more PPTs and more slides in this part only. The second question is what is heat? What is heat? When the temperature goes on increases, we called heat is generated. So it is the difference between temperature. So heat is that. What is the unit of heat? Yes, it is calorie or kilocalorie. So this is the heat. Now how the heat is transferred? As I right now I told you, it depends on the mode of transfer. Either it will be conduction, convection or radiation. So one image is there by using which you can come to know what is exactly it is. Mode of heat transfer. Okay. Conduction, convection and radiation. So this is the difference between 3 of them. I told you one picture is there which explains all the things. Yes, here is the picture. So conduction, convection and convention. Observe that pic and you can come to know what is exactly these 3 modes of transfer of heat. What is that? Fire is there. Below that fire, one container is there which is heated up. As the temperature goes on increases, molecule inside that fluid will try to move. So if we consider transfer of heat through fluid caused by molecular motion, it is called as convection. Second, conduction. As we hold that pan or hold that any material which is there on the fire, if it is a beaker and we hold that beaker, so heat will transfer from substance to another substance. It need a medium, one to another. So that is conduction. And third one is radiation. It doesn't require any medium. Heat radiates or sun radiates heat. So the energy which is coming from sun, from moon, from stars is nothing but radiation because it doesn't require any medium to come towards us. So this is radiation. Alright. So let's see the difference between 3 of them. First and main difference is in conduction, the heat transfer takes place between object by direct contact. When there is a direct contact between two material, two molecules, two substances and the heat transfer, it is called as conduction. What is convection? Convection means when the heat transferred is within the molecules. It doesn't require exact contact over there. So this is convection. And then radiation. In radiation, heat transfers Heat transfer occur through electromagnetic waves. This is very main term which is related to radiation. Electromagnetic waves are there which transfers the heat. This is the third form of or third mode of transfer of heat. Let's see the second difference between three of them. The heat transfer takes place due to difference in temperature. Obviously, if the temperature changes, then only heat will created, and then only it will try to move from one to another. So this is a very basic difference between three of them. Heat transfer takes place due to difference in temperature. In convection also this is same, and in radiation the heat transfer occur in all the object with temperature greater than 0 Kelvin. It occurs everywhere. Next point is heat transfer in conduction is very slow. In case of conduction, heat transfer is slow. In case of convection, it is faster. And in case of radiation, it is fastest. Alright. Next, the heat transfer occurs through heated solid object. In case of conduction, we have seen that picture in which you can come to know that heat transfer occurred through the heated solid object. Convection, the heat transfer occur through the intermediate object. For example, heat transfer between air and water. So this is convection. Next thing is radiation. The heat transfer occur through electromagnetic waves. That was the first point in distinguish, right? So it occurs in electromagnetic waves. And the last point, which is the difference between three of them, is it does not follow the law of reflection and refraction in case of conduction. Obviously, because there is direct contact between two materials, so it doesn't follow any law of reflection and refraction. Direct heat is got transferred to another material, so there is no law which is followed by this conduction method. Then second is in convection also it does not follow the law of reflection and refraction. But what happens to radiation? Yes, obviously it follows the laws of reflection as well as refraction. So this is all about the difference between three of them, three modes of heat transfer, which is conduction, convection and radiation. So as I have shown you the diagram, let's see again. This heat generated, so this is radiation. When it is moving towards this, it is convection. When it is in contact with this rod, so this will be conduction. So this is all about conduction, convection and radiation. I hope you all got this point. Let's moving towards next. Now we are going to see interaction of thermal radiation and matter. As I told you in some last slides, we are going to see about radiation. So before going towards this, I want to tell you, when some amount of it is got fallen on any object, does it completely absorb, or does it completely reflected, or does it completely transmitted? No, it is not completely absorbed or completely reflected or completely transmitted. Either some amount of it will reflect, some amount will transmit, and some amount will absorb. By using these terms, we are going to see something very interesting, which is nothing but this. Let Q be the total amount of thermal energy incident on the surface of object, and QA, QR and QT be the respective amount of it absorbed, reflected and transmitted by that object. So Q is the total, so that will be Q is equal to QA plus QR plus QT. Now what I am going to do is I am going to divide both the equations and both the sides by Q, and I am getting 1. Q by Q will be 1. So 1 is equal to QA upon Q, QR upon Q, QT upon Q. So this is nothing but 1 is equal to, I am going to say QA upon Q is nothing but A, QR upon Q is nothing but R, QT upon Q is nothing but T. and suffix r is there. So what is this? A, R and T. Let's see what is that. First, coefficient of absorption or absorptive power or absorptivity, and it is denoted by small a. It is nothing but ratio of amount of heat absorbed to the total quantity of heat incident. That means A is equal to QA divided by Q. Ratio of amount of heat absorbed to the total amount of heat incident. This is absorption or coefficient of absorption or absorptivity. Second is coefficient of reflection or reflectance. It is denoted by R. Same type of definition we are going to see. The ratio of amount of radiant energy reflected to the total energy incident is called coefficient of reflection. So R is QR upon Q. Next, coefficient of transmission or transmittance. So it is TR. It is nothing but amount of radiant energy divided by total energy incident or ratio of amount of radiant energy transmitted to total energy incident is called coefficient of transmission. So this is all about A, R and T. And what is the relation between them? Relation is A plus R plus T, as it is given, is equal to 1. In previous slide we have seen that. Alright, so let's move towards the another slide which will give you the explanation about if A becomes 0, what happens to the substance, if R becomes 0 and if T becomes 0, what is that substance is exactly called. So let's see. First, a substance through which heat radiation can pass. That means TR is not 0, but it is not a good reflector as well as it is not a good absorber, though it is called as diathermous substance. Try to remind this. A substance through which heat radiation can pass. Heat radiation is passing, so it is called as diathermous substance, and TR is not equal to 0. And diathermous substances or diathermous body is neither good absorber nor a good reflector. Examples are glass, quartz, sodium chloride, hydrogen, oxygen and dry air. Alright. As you can see, glass is not a good absorber nor a good reflector. Only glass. I am not saying mirror. It is glass. So it is diathermous substance. Let's see next one. Substance which are largely opaque to thermal radiation, that is, do not transmit heat radiation. It do not transmit heat radiation which is incident on it. It is known as athermenous substances. Which are they? You can tell me. These are water, wood, iron, copper, moisture and benzene. They do not transmit heat radiation incident on them. That is known as athermenous substances. So next is, if TR is 0, what happens to the relation of A plus R plus T? If TR is 0 and A is 0, A plus R plus T is equal to 1. If T and A is 0, R will be what? 1. So all incident energy is reflected by the object, that we can say. So it is a perfect reflector. And if R is 0, TR is 0, so A will be 1, so it will be perfectly black body because it is absorbing all the heat energy which is incident on it. So that is called as perfectly black body. We are going to see in detail what is exactly black body, how it can be created, and we are going to see many things which are related to this. But in basic, what is perfectly black body? In the relation of A, R and T, when R is 0, which is coefficient of reflection, when TR is 0, coefficient of transmission, then we get A is equal to 1. So that means from this equation we can say the heat energy which is incident on any object, it got absorbed totally. So this is called as perfectly black body. Okay, so this is all about the substances. What is ditherminous? When heat radiations can pass, it is ditherminous. When heat radiation cannot pass, atherminous. So this is all about this. So what we have covered today, we have seen Mayer's equation, which is Cp minus Cv is equal to R, and the modified is Cp minus Cv is equal to R upon J. Then we have seen specific heat capacities Cp and Cv in case of monoatomic, in case of diatomic, and in also case of polyatomic. Alright. Next, what we have seen? Conduction, convection, and radiation. Yes, we have seen the difference between them. And absorption, reflection, and transmission, and even the relation between three of them. And we have seen the coefficient of three of them. So this is all about we have learned today. So thank you so much for watching all the video. Do comment if you have any query regarding this. If you don't get what is there inside a slide, please let me know. I will try to solve your query very quickly. Okay, thank you so much.